Okay, so in this video we'll be talking about cubic functions. So where do we start? Now let's look at the basic cubic graph, where you're going to have a curve going from the bottom left to the top right, goes through the origin. What do we call that point of the origin? We call that the stationary point of deflection. Now we're just going to call it SPOI for short, since that's just an acronym of stationary point of inflection, and we're going to be mentioning this a little bit. So what happens here is that the gradient is 0 there, and it's going to inflect. So the gradient goes from decreasing gradually, and then it increases again. But we'll talk about more of that in calculus. So in this case over here, we just want to see how it's moving according to this formula over here. Now, if your function appears in this kind of pattern at any point, you can see that your SPOI is actually just going to move to the right by a factor of h. So if this is x minus 3, you can move to the right by 3 units. If it's x plus 3, you'll see that h is actually going to be a negative. So that if you have two negatives here, you have double negatives, so which makes it positive. So this means it's going to move to the left. And decay here has no tricks. This just states the vertical translation of your graph. Or in other words, the SPOI is going to move up by whatever value of k you have. So we're not going to be seeing SPOI in these two examples over here, but rather we'll need to find a rule through x-intercept forms. And there's a few of them that we need to recognize. So if we look at the form where there's 3 x-intercepts, you'll see that there's 3 brackets and all of them contain a linear term. So all of the x-intercepts here are going to be, well, if a x-intercept y is equal to 0, and this means that any one of these brackets has to be 0 according to null factor law. So you're either going to have x equal to n, x equal to n, or x equal to p. Very similar to how you do quadratics. And all of these intercepts are going to have your graph cut through the axis. For 2 x-intercepts, that's also possible for a cubic graph. If you ever have one of your brackets squared, this means that at this intercept over here, we have x equals to m. Instead of having the graph cut through the axis, what's going to happen is that it's going to be just touching the x-axis. So if we just draw this out real quick, and we have m over here, then what's going to happen is something like this. Just going to touch it once, or if it's coming from below, going to come through the x-axis just once at n. And of course, the other linear term doesn't have a square, it's just a bracket by itself. So it just cuts through. Alright, so let's look at these rules over here. Oh, not rules, but the graphs. We need to find a rule. So in this case over here, we can see that there's 3 x-intercepts. So how about we try using this formula over here. So first of all, we know that it's at negative 1, 0. So this one over here means that we must have x plus 1 as a linear factor. Over here, we have x minus 1 to get x equals to 1 when y is 0. And x minus 2. Okay. So y can equal to this. But remember, there's also a factor of dilation over here. So this is generally dilation away from the x-axis. We call it a. We're not sure what this is. And since we already used all of our x-intercepts, now if you slot any of these coordinates into our rule over here, you'll find out that the a value gets cancelled out as well, since one of these brackets will turn to 0. So what we do need is one other point, and conveniently we're given the y-intercept here. So let's slot that in. So we're subbing x equal to 0, y equal to 4. When we do that, get 4 equal to a times 1, negative 1 times negative 2. So the right hand side becomes 2a. So 4 equal to 2a will give you a equal to 2. And so since we've found the dilation factor now, we put that back into our rule. But we know the value of A now. And that is it for this one. Alright, so over here, now it's still a cubic. It's got that kind of shape. But what's happening here? Now, it's going the opposite direction as well. So we know it's a negative cubic since it's beginning from the top, from left to right, and then it ends off in the bottom on the right hand side. So we'll work with the A value later. It's going to be negative. And we know there's 2 x-intercepts. One at negative 3, 0, one at 3, 0. So we know there's x plus 3 for this one over here. And x minus 3 for the intercept where the graph, you can say, touches the x-axis or caresses it. Just touches it and goes. Alright, so a good way for me to remember at least, I like to think of this as a parabolic kind of intercept. So since there's this parabolic shape as it just touches the x-axis, you can also think of, what do you think of when you think of parabolas or you think of quadratics? Quadratics, we have a square. So this square over here for the bracket means that we're going to just touch the x-axis at x equals to 3. And of course, we're not sure of the dilation factor just yet, so we do need to plug in one more coordinate. So x equals to 0, y is equal to negative 27. So negative 27 is equal to 3 times negative 3 all squared. So the right hand side becomes 3 times 9. So that is 27. And so negative 27 is equal to 27a. A is negative 1. And that's where we also account for the reflection in the x-axis as well. This dilation factor here already tells you. And so our rule is negative 1, so we just put a negative there, times x plus 3 times x minus 3 squared. Don't forget about that one. If you don't have a square here, it's just a quadratic rule.